Hi everyone. In this chapter 7, we are going to study about the design of column. This is just a cover page, but this cover page contains a pretty good picture about tie and spiral. Tie and spiral in columns is to resist shear force, like the stirrup in beam. So that stirrup, tie, spiral all are to resist shear forces. In addition to that, tie and spiral in column will protect the main rebar from buckling at time of column failure. So that in seismic area, the role of tie and spiral are very, very important. Another role of tie and spiral is to keep the concrete debris, crushed concrete, within them, and it will give increase in ultimate strength of column at time of final failure. Let's look at load path. Usually load is applied on the slab, and the slab is supported by beams, and the beams are supported by big beams or girders. Girders are usually supported by column, and the column transmits their load to foundation, eventually to soil. If you look at the load type, it could be concentrated load, or they may call it point load. If there is a wall, it will constitute a line load. But mainly, loads are applied to the slab in form of surface load or area load. The load is transferred to the beam or girder as a line load. And then they are transferred through column as concentrate load or as a point load, and then footing or foundation to the ground. In this load path, the consequence of failure of column is very, very critical, because failure of column or columns may lead to collapse of the entire structure. So you may see slab failure or beam failure may be localized, but failure of columns can be very, very catastrophic. As you saw in 911 case, the Twin Tower failed due to column failure. Okay, let's look at several compression members. First compression members that we learned is compression member in truss. All truss members are either tension or compression. Top chord will be compression under gravity load. And these days another compression members are there. And we call these members as diagrid. So that the members in diagrid is usually in compression. And there is a load bearing walls. In this picture, this column is actually compression member, but we'd like to look at the walls. Walls are load bearing in this application, and they are compression members. And of course, column is in compression. And usually we limit our column to the vertical. Compression member truss can be skewed. Diagrid usually, if not generally, they are skewed. Load-bearing walls and columns are usually vertical. Classification of columns. The first classification is stocky column. As you see here, only axial force is applied. Second classification is short columns. The term stocky and short will not ring your bell pretty much, so that you need to be very careful. If the technical terminology is not impressive, then it's hard to memorize. So they forget it so easily. Short column will receive certain amount of axial force and some bending moment. Okay, memorize it. And the third class is slender columns. Slender, critically important terminology in structural engineering. And if I use the concept of slenderness ratio for this classification, the slenderness ratio for slender columns somewhere around 200, for example, then stocky columns will have slenderness ratio of somewhere around 30-40, and the stocky columns, short column is in between. So in slender columns, bending moment will control the design as compared to smaller axial force capacity. Stocky column will receive axial stress only, so that the only formula that you need to know for stocky column is sigma equal P over A. A short column will receive, in addition to axial stress, we are going to have primary bending stress. Okay. Well, what is primary bending stress? Primary bending stress is bending moment from bending moment diagram. As compared to that, slender column will receive axial stress, primary bending, and more importantly, secondary bending stress due to buckling phenomena. So that in addition to this linear combination, we are going to consider buckling effect. In short column case, axial stress, of course, axial stress is normal stress, right? And normal stress due to bending can be linearly combined using principle of superposition. But there is no simple way to combine these two with buckling effect. So buckling analysis must be done. And that is not a real easy thing, and it's very, very time consuming. Anyway, that is out of scope of this class. So we are not going through the slender column. But anyway, the classification of column is like this. And we are going to pay attention to this one. So if your column is very slender, as we learned, buckling failure is expected, not material failure. And for short column, there is no secondary stress due to buckling, also material failure is expected, and majority of RC column will fall in this category. Of course, static column will go through material failure. For example, crushing. Okay, let's talk about types of columns. As we saw in the cover page, there is two types in RC columns. First, tied column. Second, spiral columns. Main difference between tied column and spiral column is spiral is continuous, but ties are disconnected, as we saw in stirrup design. Ties or spiral will connect longitudinal main rebar together so that it can protect main rebar from buckling at time of failure. And that type of failure mode is very important in seismic zone, so that even though spiral columns are more expensive, but it's more ductile, so that spiral columns are used mainly in seismic region. Tied column also is used in seismic region, but its capacity is less than spiral columns. Because of the spiral continuity, it's hard to construct, so it's more expensive. But its final behavior at ultimate situation is excellent. Okay, a column is for axial force. Naturally, axial strength of column is our main concern. Axial strength of concrete is 0.85 FC prime. This may sound familiar, but actually this is not. Whitney stress block factor. The number is the same. So anyway, it's 0.85 FC prime. Axial strength of concrete. Axial capacity of concrete will be concrete strength or stress times area. This will give you axial force or axial capacity of concrete. Axial strength of steel is Fy. If you recall, axial strength and tensile strength of steel is the same Fy. So if you use Fy of 60 ksi, its axial strength will be 60 ksi too, even though 60 came from tensile test of steel, but we know in compression and in tension, steel strength is the same. Okay? If you are not familiar with that, memorize it. So that axial force of steel or axial capacity of steel will be steel strength or stress times steel area. So in that regard, nominal capacity of reinforced concrete column will be 0.85 FC prime concrete strength times concrete area plus steel strength times steel area. In this formula, basic concept is in beam, steel take tension force and concrete take compression force. But in column, they are just doing the same. all are resisting compression force. Unless buckling effect comes so that one side is in tension, different story. But in usual column, concrete will resist compression force and steel will resist compression force too. Actual capacity of columns is introduced like this from previous page, or you may see your concrete area as gross cross-section of column minus steel area. This is more convenient instead of going this way. So what is a gross area of column? That is nothing but B times H. We need to consider accidental eccentricity because no column is perfectly straight and no load is 100% concentric. So there is certain amount of eccentricity. So to consider that eccentricity, we are going to consider alpha factor. Phi factor was strength reduction factor or resistance factor. Alpha factor is eccentricity factor. Okay, memorize it. Why do we use eccentricity factor for 0.8 for tight column and 0.85 for spiral column is that if you want to consider the eccentricity moment, then your calculation will be a lot harder. So instead of going through rigorous analysis, we are going to just use a bit more material by adopting alpha factor. And then we do not calculate the moment effect. We do not even calculate moment. We just use actual force and we just use alpha factor for a design point of view. Okay, so ACI strength of RC column is given by this formula. This is what we have discussed in the previous page, and alpha factor 0.8 and 0.85 for tight column and spiral columns respectively, and we are going to call it eccentricity factor. Okay, memorize it. And of course we are going to have Phi factor, strength reduction factor, and there will be 0.65 for tight column. Why is this so small? Because we consider consequence of column failure. Consequence of column failure is a lot severe than failure of beam or slab. And 0.75 for spiral columns, because spiral columns are more expensive, but it's more ductile. Its capacity is higher. Okay, and we are going to use this formula if your eccentricity moment is small. If you have eccentricity, then we are going to have eccentricity moment. The magnitude will be P times E. So you can express eccentricity as M over P. We are going to use this relationship a lot in this chapter. So instead of this, why don't you familiar with this? Okay, why don't you get familiar with this relationship? Of course, that is from this one, but we are going to use this one a lot more from now on. So if you have small eccentricity moment, then we are not going to go through rigorous bending analysis. We do not even calculate bending moment. We just apply this formula and we are going to use this p factor in addition to this alpha factor. Then you need to know what is definition of sufficiently small, how small it is. If your E value is 0.1 h, memorize m over p, or E value must be smaller than 0.1 h. Then do not do bending analysis, just use this formula. HI recommend to use this formula if your eccentricity is smaller than 0.1 h. Please note that your h is least dimension of your column. Okay, in summary, HI strength of RC column is like this, and P factor is 0.65 for tight column and 0.75 for spiral columns. And why these resistance factors are so small? First, consequence of column failure. Beam failure may be localized, but column failure may lead to collapse of entire building. As you saw, collapse of World Trade Center building. And the column is a lot difficult to construct as compared to beam construction or slab construction. Because column is smaller dimension and there are so densely spaced rebar inside formwork, so that segregation of concrete may occur. Segregation is, coarse aggregate goes separately and cement paste goes separately, so that the concrete strength is a lot smaller than a cylinder test. So because of all these, consequence of failure and construction difficulties and segregation and bleeding of concrete in the formwork, all those will cause smaller P factors. And this will come up when you take FE exam. So this is pretty much important. Here I tabularized the HI code requirements for column. All these values and all details must be memorized to pass FE exam. Minimum steel ratio is 1% and maximum steel ratio is 8%. But practical maximum is 5%. If you use more than 5%, if you look the column from top before casting concrete, it will be so congested, so that there is no way, no practical way to place concrete properly without having honeycomb. So that even though ACI allows 8%, do not use 8%. If go over 5%, get alert, because construction quality may be different from your blueprint. Minimum number of bars is 4, because if it's rectangle or square, then each corner must have a rebar, so that at least 4. And if it's a spiral, then it will be 6 minimum. If it's a triangular shape, definitely it's 3. So minimum size of ties, as is true in design of stirrup, mainly we are going to use number 3 or number 4. If main rebar is number 10 or smaller, then you are going to use number 3 tie. If it's larger than number 10 rebar, then you are going to use number 4 stirrup or ties. And tie spacing and lateral support, clear spacing, that will be explained while we are solving the example problems.